Welcome to my projectbazaar.com.
Yeah, let us discuss about the channel and power adaptation for cognitive radios in multi-user OFDM systems. Yeah, let us discuss about the abstract of the product. So in this proposed works to investigate the joint power and channel allocation problem for the OFDM, so that is orthogonal frequency division multiplexing based on the multi-user cognitive radio systems. So to improve the quality of service, that is QoS, in terms of signal to interference pulse noise ratio, so that is SINR, and proportional rate constraints. Since the joint subcarrier and power allocation problems is a convex integer problem, and the closed form is solution too difficult to find it. The quality of service requirement of each cognitive user improved by its minimum SINR, and interference introduced by the unlicensed secondary users to the primary users make power and channel allocation problem more complex. So that is finally to analyze the results obtained from the simulations to calculating the QoS in terms of signal to noise interference. Moreover, because of the static spectrum allocation by licensed bodies to service providers for exclusive use of long time and vast geographic area, so there are more useful frequency bands left for further development of wireless service and applications. As a consequence, if the problem is left understood, and many wireless service provider will be facing spectrum storage. So the optimal spectrum access using cognitive radio technology is an emerging concept for an efficient utilization of radio frequency spectrum by allowing unlicensed spectrum to secondary users to access the licensed spectrum without causing harmful interferences to the licensed primary users. So in a dynamic spectrum access, secondary users are required to either sense a channel and identify the ideal bands, or search them on the geolocation database to access the licensed band. So the note that the spectrum sensing is an essential step in the DSA, so which has been well studied, and the readers also refers to that. And then the reference and their inner details. Finally, to analyze the results obtained from the simulation. Yeah, let us discuss about the flow diagram of the product. So first of all, get the input signal. The input signal, we will take the GSM signal, so that is a GSM band of signals, and then filtering the PF, so that is a band pass filter. By using the input signal to reduce the noise by using the BPF, so that is a band pass filter, and then A to D converter. So in this process, A to D converter analog to digital converter of the pre-processed signal by using the BPF filter, and then following to this FFT. So FFT means fast Fourier transform. By using the digital converter, the signal is converted to digital, and then 0 and 1, so that is processing by the Fourier transform, and then the squaring device. In the Fourier transform, the equivalent circuit is calculated by the squaring, so the FFT values is calculated as squaring, and then finally get at the integrator value, taking the square value and then the integrating, and then also going for the windowing. So in this process, windowing, we use a Hamming window. There are different type of windowing, hand and Hamming windows. So here we use the Hamming window process by using the integrated value, and then FFT magnitude. So here we using the FFT, so that is a fast Fourier transform. In this block, we take the magnitude of the fast Fourier transform value, and then going for the threshold. So in the FFT magnitude value, we calculating the threshold. So threshold value is some condition or display. For greater than 0.1, it's take a primary user to allow the channel. If less than the 0.1, the secondary users allow to the channel. So this is a processing of threshold. By using the FFT magnitude, the process is calculated by using the threshold. So that is, for example, greater than 0.1, so here we are using the secondary values are presented. Less than 0.1, here we the primary value are presented. So this is the threshold value of the processing, and then finally getting the output signal. So output signal, we calculated the process of FFT by using the value of output signal. Finally, the performance analysis, bit rate, and then SINR, so that is a signal to noise ratio, and then SINR, signal interference noise ratio, by calculating the reduce of the bit rate. So finally, the performance analysis by calculating the bit rate, SINR, and then outage probability of the process by using the output signal. So these are the overall flow diagram of the process. Let us discuss about the running procedure for the product. So click the main file and then run. So the guide design will be open. So this is the guide design of the error rate analysis of the cognitive radio transmission. So click the file and then import the signal. So here we using the imported signal as GSM signal. So GSM signal we will take and then open. So this is the input signal for the GSM band. So this is the frequency represented as a hertz, so 0 to 1000, and this is the power by frequency dB per hertz. So that is a decibel and 10 to 90. So this is a decibel of the signal. So this is the input signal, and then pre-processing. In the pre-processing, applying the filter. So there is a band pass filter we have to apply. So here we using the band pass filter, and then the noise will be reduced by the using of the input signal. So that is the input GSM signal of the frequency. So this is also a frequency and power frequency of dB by hertz. And then PD versus PF. So that is the energy reduction probability. So probability of false alarm and probability of reduction. So that is a PD and PF. So probability of false alarm and probability of reduction using the energy reduction by using the 0 to up to 1. So this is the probability of false alarm, probability of reduction, and then periodogram. So the periodogram we are applying the Hamming window by using the plot using the FFT and NFFT. So in the x-axis is the frequency of hertz, and in the y-axis power divided by frequency divided by hertz. So by using the periodogram plot, we using the Hamming window and plotting the represent the signal for the GSM band signal. So and then Welch. So in the Welch condition we will click, and so this is an inbuilt function. So the Welch will be represented. Let's take some time to represent the Welch process. So this is the Welch plot using the FFT and NFFT for the GSM band signal. So this is the frequency and also frequency hertz. And finally calculating the error rate comparison. So here we are using the error rate comparison. There are different error rates. So there is a conventional error function and conventional code and forward correction code. So this is our proposed. So these are the different bit error rate comparison for the probability of bit error and the signal power. So this is in x-axis that take signal power, and the y-axis take the probability of bit error. So these are the bit error rate comparison of conventional error function, convolutional code, and forward error correction code of the process. So these are the encoded data. So this is our table. So these are the encoded data. So up to how much encoded data are presented. So this is the sender data. So how much sender and that is transmitted data are sent, and then this are the receiver data, and finally calculate the value of probability of transmission error and then probability of noise. So these are overall running procedure for the product.